Hello, in this lecture we will prove Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its Theorem. In the drawing we have a triangle ABC. In triangle ABC, the length of side AB is units, side AC equals to B units in its length, and side BC equals to A units in its length. In addition, line segment BD equals to M units, and line segment DC equals to N units in its length. And the Theorem in this triangle ABC, is line segment AD. And in the length of the Theorem AD is D. That is to say, line segment AD equals to 2 units in its length. And I repeat again that Stewart's theorem yields a relation between the lengths of the sides of the triangle to the length of its Theorem, the Theorem AD. Okay, the length of the Theorem AD is D units. And according to Stewart's theorem, the following equation is true, that b squared times m plus c squared times n equals to a. We open brackets, inside the brackets we have d squared plus m times n. I repeat again, b squared m plus c squared n equals to a. We open brackets, inside the brackets we have d squared plus m times n. So we prove that this equation, Stewart's theorem, is true in two different methods. We start with the first method. In the first method, from point A, from the vertex A, we draw perpendicular on BC. Okay. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. We define the length of side line segment ED as X. Line segment AE will be equal to edge units in its length according to our definition. What is the length of line segment EC? EC equals to ED plus DC. ED is X and DC is N. So, in conclusion, EC equals to X plus N. EC equals to X plus N. And what is the length of this line segment BE? From the drawings, it's very easy to see that BE equals to BD plus ED. Again, BE equals to BD plus ED. BD equals to M units, ED equals to X, therefore, in total, BE equals to M minus X. This line segment BE equals to M minus X units in its length. Here I write it down that BE equals to BD minus ED. So BE equals to BD, that is M, minus ED, that is X. So B equals to M minus X. Okay. In the next step, we'll implement the Pythagoras theorem on the right green triangle AED. Okay. So, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. I repeat again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here, by PT is a relation from Pythagoras theorem. The hypotenuse in the right green triangle AED is AD. Therefore, the square of the hypotenuse is AD square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE square plus ED square. Okay, again, according to the Pythagoras theorem, in the right green triangle AD square equals to AE square plus ED square. Okay, so AD equals to the unit itself, therefore AD square is D square, and it is equal to AE square. AE equals to H, therefore AE square is H square plus ED square. ED equals to X, therefore ED square is X square. In conclusion, we found out that according to the Pythagoras theorem, in the right green triangle AED, D square equals to H square plus X square. In the next step, we will implement the Pythagoras theorem on the right triangle AEC. On the right triangle AEC, by PT is a relation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle AC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC square, and it must be equal to the sum of the squares. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE square plus ED square. So, according to the Pythagoras theorem, we found out that in the right triangle AC square equals to AE square plus ED square. This is actually equation number 1. Okay, so here we have AC square. AC is B, therefore AC square is B square, and it is equal to AE square. AE is H, therefore AE square is H square plus EC square. Repeat again according to the Pythagoras theorem. In the right triangle, triangle AC square equals to AE square plus EC square. Repeat again. AC square equals to AE square plus EC square. We found out that AC square is B square, AE square is H square, and finally plus EC square. EC, here, line segment EC equals to X plus N units, therefore EC square is X plus N square. So in conclusion, we found out that according to equation number 1 and Pythagoras theorem, B square equals to H square plus X plus N square. Here we'll open the brackets on this side of equation number 1, and we found that according to equation number 1, B square equals to H square plus X plus N square equals to X square plus N square plus 2 times Xn. In this equation number 1, we have the expression X square plus H square plus X square, and we already found out that H square plus X square equals to D square. So we substitute D square in this equation number 1. We substitute H square plus X square in this equation number 1 by D square. Okay, and we get that here B square equals to H square plus X square is D square plus N square plus 2 times Xn. In the next step, we will implement the Pythagoras theorem on triangle AEB. Okay, again, we will implement the Pythagoras theorem on the pink triangle, triangle ABE. Okay. So in the pink triangle, triangle AEB, or PT, and we do the Pythagoras theorem, we'll get that the square of the hypotenuse is a B square, or the hypotenuse is AB, therefore the square of the hypotenuse is AB square. And it must be equal to the sum of the sides of the perpendiculars, that is to say it must be equal to AE square plus BE square. Repeat again. In the right pink triangle, triangle AEB, according to the Pythagoras theorem, AB square equals to AE square plus BE square. So AB is C, therefore AB square is C square, and it is equal to AE square. AE is H, therefore AE square is H square plus BE square. BE equals to M minus X, therefore BE square is M minus X square. So according to the Pythagoras theorem, in the right triangle, right pink triangle, triangle AB, C square equals to H square plus M minus X square. We'll open the brackets on this side of equation number 2 and we get that according to equation number 2, c squared equals to h squared plus m minus x squared equals to, according to the algebraic identity, that a minus b squared equals to a squared plus b squared minus 2 times ab, we get that m minus x squared equals to m squared plus x squared minus 2 times m times x. We have already found out that h squared plus x squared equals to d squared here. Therefore, we substitute h squared plus x squared in this equation, equation number 2, by d squared. And we get that c squared equals to h squared plus x squared is d squared plus m squared minus 2 times mx. This is equation number 2. And we have already found out that according to equation number 1, b squared equals to d squared plus n squared plus 2 times x times n. In the next step, we'll create equation number 3 in the following way. First of all, we'll multiply equation number 1 by m. In the second step, we'll multiply equation number 2 by n, and then we add the two equations together with each other. This will be equal to equation number 3. We'll do it in 2 steps. In the first step, generally, we will multiply, first of all, the right side, and then we multiply the left side. Okay? We multiply the right side of equation number 1 by m. This is the right side of equation number 1. We multiply it by m. So m is inside the brackets. We have d squared plus n squared plus 2 times x n plus we multiply in the second step the right side of equation number 2 by n. This is the right side of equation number 2 and we multiply it by n. So n times, inside the brackets we have d squared plus m squared minus 2 times m times x. Okay, and it must be equal to the multiplication of the left side of equation number 1 by m. In the left side we have only b squared, so it is mb squared plus the multiplication of the left side of equation number 2 by n. So it is n times, in the left side of equation number 2 we have only c squared, so it is in total nc squared. Okay. In the next step, we'll open the brackets on this side of equation number 3. And we get that according to equation number 3, we have here m times d squared is md squared plus m times n squared is mn squared plus m times 2xn is 2xmn. In the next step, we'll open the brackets of this expression. So we will have n times d squared is nd squared plus n times m squared is nm squared plus n times minus 2mx is minus 2xmn, and it must be equal to must be equal to mb square plus nc square. So actually this is equation number 3 after we open the brackets. We have, in this side of equation number 3, we have plus 2xmn minus 2xmn is 0, so those two expressions will get cancelled. What is left from equation number 3 after we cancel the two expressions? What is left is that in this side of equation number 3 we have md square plus mn square plus nd square plus nm square equals to mb square plus nc square. In the next step, we take out the square as a common factor from this expression and also from this expression. So this square is taken out as a common factor. What is left from md square after we took from md square as a common factor? What is left is actually n. What is left from nd square after we took from it this square as a common factor? What is left is actually n. Plus, then we take out mn as a common factor from this expression and also from this expression. So what is left from nm square after we took from it mn as a common factor? What is left is actually m, and what is left from mn square after we took from it mn as a common factor? What is left is actually n, and it is equal to mb square plus nc square. In the next step, we take out m plus n as a common factor of those two expressions. M plus n is taken out as a common factor, so what is left from this square times m plus n after we took from it m plus n as a common factor? What is left is actually this square. And what is left from n times m plus n after we took from it m plus n as a common factor? What is left is actually mn. And it is equal to mb square plus nc square. Actually, m plus n equals to a. It is very easy to see it from the drawing. According to our definition, BC equals to A from one side, but BC from the drawing it is very easy to see that BC also equals to BD plus DC, of course. BD equals to M, DC equals to N. So in total, BC equals to M plus N from one side. From the other side, it is equal to A. So therefore, M plus N equals to A. Okay, therefore M plus N equals to A. So we substitute m plus n in this equation number 3 by a, and we get that according to equation number 3, m plus n is a, and inside the brackets we have d square plus mn that is equal to b square m plus c square n. And this is exactly Stewart's equation. So we prove Stewart's equation. according to the first method. In the next step, we'll prove Stewart's equation in the second method. In the second method, we will define angle ADB. This angle is theta. Therefore, the adjacent angle ADC must be equal to 180 degrees minus theta. According to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. BC is a straight line. Therefore, the sum of the angles on the upper side of the straight line BC and point E must be equal to 180 degrees. So which angles we have here? We have angle, this angle, that is angle theta, plus the missing angle ADC must be equal to 180 degrees. Therefore, the missing angle must be equal to 180 degrees minus theta, because 180 degrees minus theta plus theta equals to 180 degrees, exactly according to rule number 1. Okay, in the next step, we'll implement the law of cosines on the green triangle ADB, and then we'll implement the same law of the law of cosines on the pink triangle ADC. I will remind you quickly what is the law of cosines. First of all, the law of cosines is true in any triangle. So here we have triangle ABC that could be any triangle. The length of side AB is A units, side AC equals to B units in its length, side BC equals to C units in its length. And this angle BAC equals to theta. Then according to the law of cosines, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. If we add to this equation 2 times AB cosine theta, we get this expression. Then we subtract from this equation C squared, and we get that A squared plus B squared minus C squared equals to 2 times AB cosine theta, and then we divide this equation by 2AB, and finally we get that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So we implement the law of cosines in the green triangle ADB. In the green triangle ADB or ABD, according to the law of cosines, we get that cosine theta equals to d squared plus m squared minus c squared over 2 times d times m. Okay, so actually this equation number 1, is the implementation of the law of cosines in the green triangle, triangle ABD. Cosine theta equals to d squared plus m squared minus c squared over 2 times d times m. In the next step, we'll implement the law of cosines in the pink triangle, triangle ADC. So actually, according to the law of cosines, in the pink triangle, triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times d times n. So actually, this equation number 2 is the implementation of the law of cosines in the pink triangle, triangle ADC. We have the trigonometric identity that states that cosine 180 degrees minus theta equals to minus cosine theta. Again, cosine 180 degrees minus theta equals to minus cosine theta. So we can substitute cosine 180 degrees minus theta in this equation number 2 by minus cosine theta. We'll do it now and we'll get that minus cosine theta equals to d squared plus n squared minus b squared over 2 times d times n. Okay? This is equation number 2. In the next step, we will multiply this equation number 1 by minus 1. And we'll get that according to this equation number 2, equation number 1, cosine theta times minus 1 is minus cosine theta. And it is equal to minus, inside the brackets we will have d squared plus m squared minus c squared over 2 times d times m. So actually we have two different expressions for minus cosine theta. Therefore we create equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Okay? So minus cosine theta according to equation number 1 equals to minus d squared plus m squared minus c squared over 2 times d times m. And it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 equals to d squared plus n squared minus b squared over 2 times d times n. Okay. In the next step, we'll multiply this equation number 3 by 2d. And we get that according to this equation number 3. So we multiply this side of equation number 3 by 2d. So here we have 2d over 2d is 1, 2d will get cancelled. So in the denominator we have to leave m, and the numerator didn't change. That is to say, it remains minus d squared plus m squared minus c squared. we'll multiply also the other side of this equation number 3 by 2d. Again, 2d over 2d is 1, so 2d will get cancelled. Therefore, in the denominator, we left only, in the denominator of this side of equation number 3, we left only with n. The numerator didn't change. That is to say, it remains d squared plus n squared minus b squared. In the next step, we'll cross multiply this equation number 3, and we'll get that according to equation number 3, here we'll have minus n. Inside the brackets, we'll have d squared plus m squared minus c squared. And the other side, we'll have here m times, inside the brackets we have d squared plus n squared minus b squared. So actually, this is equation number 3 after we cross multiply it. In the next step, we'll open the brackets on both sides of this equation number 3, and we'll get that according to equation number 3, we have, in this side of equation number 3, we'll open the brackets here, minus n times d is minus nd squared, plus minus n times m squared is minus nm squared, and finally minus n times minus c squared is plus nc squared. Why? Because minus times minus is plus, and it is equal on the other side of equation number 3. Here we'll also open the brackets, so m times d squared is md squared, plus m times n squared is mn squared, and finally m times minus b squared is minus mb squared. In the next step, we will multiply equation number 3 by, and we will add to this equation number 3 nd squared, first of all. So in this side of equation number 3, we have nd squared minus nd squared is 0. Then we will also add to this equation number 3 nm squared. So in this side of equation number 3, we have nm squared minus nm squared is 0. And finally, we also subtract from this equation number 3 nc squared. So it is minus nc squared. And in this side of equation number 3, we have nc squared minus nc squared is 0. So in this side of equation number 3, we left with 0. Okay. And what about the other side of equation number 3? In the other side of equation number 3, we have already had this expression, so we'll copy it as it is. Md squared plus mn squared minus mb squared. And we have also to add to this side of equation number 3 and this square, we also have to add to this side of equation number 3 nm squared. And we have to subtract from this side of equation number 3 nc squared. Okay. In the next step, we take out this square as a common factor from this expression and from this expression. So this square is taken out as a common factor inside the brackets, md square. What is left from it after we took from it d square as a common factor? What is left is m plus nd square. What is left from nd square after we took from it d square as a common factor? What is left is actually n. In the next step, we'll also take out a common factor m times n from this expression and from this expression. Okay, so what is left from nm square after we took from it nm as a common factor? What is left is m. What is left from mn square after we took from it mn as a common factor? What is left is n. And it is equals to minus, we have minus mb square minus nc square, and it is equal to 0. In the next step, we will add to this equation number 3, mb square and also nc square, and we get that d square m plus n plus mn m plus n equals to mb square plus nc square. Okay, in this side of the equation we had 0, therefore now after we added mb square and nc square, it will be mb square plus nc square. In the next step, we'll take out m plus n as a common factor from those two expressions. So what is left? M plus n is taken out as a common factor. What is left from d square times m plus n after we took from it m plus n as a common factor? What is left is actually d square, and what is left from m plus n times mn after we took from it m plus n as a common factor? What is left is actually mn, and it is equal to b square m plus c, b square m plus c square n. In the first method, we have already found out that m plus n equals to a, therefore we substitute m plus n by a here on this side of equation number 3, and we get that according to equation number 3, m plus n is a, and inside the brackets we have here d square plus m times n, and it is equals to b square m plus c square n. And this is exactly Stewart's theorem. Okay, so we succeeded to prove Stewart's theorem in the second method. In the next step, I'll summarize the lecture. We start with the first method, of course. In this lecture, we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides of the triangle to the length of its CVN. I repeat again. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. Here we have triangle ABC. The length of side AB is units, the side AC equals to units in its length, and side BC equals to units in its length. In addition, we know that line segment BD equals to m units, and line segment DC equals to n units in its length. And here, the CVN in this triangle ABC is a line segment AD. The CVN is AD, and the length of the CVN AD is d units. So, repeat again that Stewart's theorem yields a relation between the lengths of the sides in the triangle and the length of its CVN AD. Okay, and according to Stewart's theorem, the following equation is true that b squared times m plus c squared times n equals to a. We open the brackets, inside the brackets we have d squared plus m times n. Again, b squared m plus c squared n equals to a. Inside the brackets we have d squared plus n times n. We prove this equation in two different methods. In the first method, from point A we draw perpendicular on BC. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. Then we define line segment ED, this line segment as X. We defined line segment AE as H. So here EC equals to X plus N. Line segment EC equals to X plus N. And line segment BE equals to BD minus ED. BD is M, ED is X, so therefore BE equals to M minus X. Line segment BE equals to M minus X. Then we implemented the Pythagoras theorem on the green right triangle, triangle AED. According to the Pythagoras theorem, in the green right triangle AED, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AED, therefore the square of the hypotenuse is AED. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE square plus ED square. Repeat again. According to the Pythagoras theorem, in the right green triangle AED, AD square equals to AE square plus ED square. Okay, here the hypotenuse AD equals to D, therefore AD square is D square. AD square is D square. Then AE equals to H, therefore AE square is H square. AE square is H square, and finally line segment ED equals to X, therefore ED square is X square. ED square is X square. Then we implemented the law of cosines in the right triangle AEC. According to the law of cosines in the right triangle AEC, AC square equals to AE square plus EC square. Again, AC square equals to AE square plus EC square. We repeat again. In the right triangle AEC, AC square equals to AE square plus EC square. Okay. The hypotenuse AC equals to the unit inside, therefore AC square equals to B square. AC square equals to B square. AE equals to H, therefore AE square is H square. And finally, EC equals to X plus N, therefore EC square is X plus N square. EC square is X plus N square, so in conclusion, found out that according to Pythagoras theorem, in the right triangle AEC, B square equals to H square plus X plus N square. We opened the brackets on this side of equation number 1 and we found out that B square equals to H square and X plus N square equals to X square plus N square plus 2 times Xn. We already found out that H square plus X square equals to D square. Here, therefore, we substitute H square plus X square in this equation number 1 by D square. And we got that according to equation number 1, B square equals to H square plus X square is D square plus N square plus 2 times Xn. So this is equation number 1. Then we created equation number 2 by implementing the Pythagoras theorem on the right pink triangle, triangle AEB. In the right pink triangle AEB, according to the Pythagoras theorem, AC square equals to AE square plus EB square. Again, AB square equals to AE square plus EB square. Repeat again. In the right pink triangle AEB, AB square equals to AE square plus EB square. AB equals to C, therefore AB square is C square. AE equals to H, therefore AE square is H square. And finally, BE equals to M minus X. Here, as you can see, therefore BE square is M minus X square. BE square is M minus X square. So, in conclusion, found out that according to Pythagoras theorem in the right between triangle AB, C square equals to H square plus M minus X square. We open the brackets on this side of equation number 2 and found out that according to equation number 2, C square equals to H square and M minus X square equals to, according to the algebraic identity, that A minus B square equals to A square plus B square minus 2 times AB. We get that M minus X square equals to M square plus X square minus 2 times MX. We have already found out that A square plus X square equals to D square here. Therefore, we substitute A square plus X square by D square. And we got that C square equals to H square plus X square is D square plus M square minus 2 times MX. And we already found out that according to equation number 1, B square equals to D square plus N square plus 2 times X times N. Then we created equation number 3 that states, we created equation number 3 in the following, in the following steps. In the first step, we multiply the equation number 1 by M. In the second step, we multiplied equation number 2 by N. Then we added the two equations with each other, and this is equal to equation number 3. Again, we did the multiplication also in 2 steps. First of all, we multiplied the right side of this equation number 1 by M. This is the right side. So it is M times D square plus N square plus 2 times XN. Then we multiplied the right side of equation number 2 by N. This is the right side of equation number 2, so it is N times D square plus M square minus 2 times MX, and it must be equal to the multiplication of the left side of equation number 1 by M. In the left side we have only B square, so it is MB square plus the multiplication of equation number 2 by N. In the left side of equation number 2 we have only C square, so it is NC square. Okay? Then we open the brackets on this side of equation number 3 and found out that here M times D square is MD square, N times N square is MN square, and finally M times Xn is M times 2xn is 2xmn. And then we open the brackets here also. N times D square is ND square, N times M square is NM square, and finally N times 2mx, M times minus 2mx is minus 2mxn. And it is equal to MB square plus NC square. So actually, this is equation number 3 after we open the brackets. Here we have 2xmn minus 2xmn is 0, so those two expressions will get cancelled, and we left only with mb square plus nm square plus n square plus mn square equals to mb square plus nc square. Then we took out this square as a common factor from nd square and from md square, and so inside the brackets we left only with m plus n. Then we took out nm as a common factor from mn square and also from nm square, so inside the brackets we left only with m plus n. And it is equals to mb square plus nc square. Then we took out m plus n as a common factor from those two expressions, so inside the brackets we left only with d square plus mn, and it is equal to mb square plus nc square. Here m plus n equals to a. It is very easy to see from the drawing. Side BC, from one side it is equal to m plus n. From the other side BC equals to a, therefore m plus n equals to a. So we substitute m plus n in this equation number 3 by a, and we got that m plus n is a. Inside the brackets we have d square plus m times n, that is equal to b square m plus c square n. And this is exactly Stewart's theorem. So we proved Stewart's theorem according to the first method. In the next step, we actually proved Stewart's theorem in the second method. In the second method, we defined this angle ADB is theta, therefore the adjacent angle ADC, this angle must be equal to 180 degrees of theta according to rule number 1, that the sum of the angles on one side of a straight line is equal to 180 degrees. Then we implemented the law of cosines in this great triangle, triangle ABD, in this pink triangle, triangle ADC. I will remind you shortly what is the law of cosines. First of all, the law of cosines is true in any triangle, so this triangle, triangle ABC, could be any triangle. We know that the length of side AB is A units, side AC equals to B units in its length, and side BC equals to 3 units in its length, and this angle BAC equals to theta. Then, according to the law of cosines, the following equation is true. C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, then we added to this equation, to the law of cosines, this equation that is the law of cosines, we added 2 times AB cosine theta, and we got that 2 times AB cosine theta plus C squared equals to A squared plus B squared. Then we subtracted from this equation C squared, and we got that 2 times AB equals to A squared plus B squared minus C squared. And finally we divided this equation by 2 times AB. We got that 2 cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So we implemented the law of cosines in the green triangle, triangle ADB. According to the law of cosines in the green triangle, triangle ADB, cosine theta equals to D squared plus M squared minus C squared over 2 times D times M. I repeat again, according to the law of cosines in the green triangle, triangle ADB, cosine theta equals to D squared plus M squared minus C squared over 2 times D times M. In the next step, we implemented the law of cosines also in the pink triangle, triangle ADC. According to the law of cosines in the pink triangle, triangle ADC, cosine 180 degrees minus theta equals to D squared plus N squared minus B squared over 2 times D times N. Repeat again, according to the law of cosines in the pink triangle, triangle ADC, cosine 180 degrees minus theta equals to D squared plus N squared minus B squared over 2 times D times N. We have the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta. Therefore, we substitute cosine 180 degrees minus theta in this equation number 2 by minus cosine theta, and we got that minus cosine theta equals to D squared plus N squared minus B squared over 2 times D times N. Then we multiply this equation number 1 by minus 1, and we got that cosine theta times minus 1 is minus cosine 1, and then we multiplied also this side of equation number 1 by 1, so it is minus, and here this expression we put in brackets, so inside the brackets we have D squared plus M squared minus C squared over 2 times D times M. Then we created equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2, very simple. So minus cosine theta according to equation number 1 equals to D squared plus M squared minus C squared, and it must be equal to minus cosine theta according to equation number 2, that is equal to D squared plus N squared minus B squared over 2 times D times N. Then we multiply this equation number 3 by 2D, and we got here 2D over 2D is 1, so 2D will get cancelled, and we left only with M in the denominator. The numerator didn't change. It stays as minus D squared plus M squared minus C squared. Then we multiplied also this side of the equation by 2D. 2D over 2D is 1, so in the denominator we left only with N. The numerator didn't change. It stays as D squared plus N squared minus B squared. Then we cross multiplied this equation number 3, and we found out that according to equation number 3, minus M times D squared plus M squared minus C squared equals to M D squared plus N squared minus B squared. Then we open the brackets on both sides of this equation number 3, and we found out that here N minus D squared is minus N D squared, and n minus m square is minus nm square, and minus n times c square is plus nc square. Why? Because minus times minus is plus. Then we open the bracket also on this side of equation number 3 and found out that according to equation number 3, m times d square is md square, plus m times n square is mn square, and finally m times minus b square is minus mb square. Then we added to this equation and this equation number 3 and d square. So nd square minus nd square is 0. Then we added also nm square. nm square minus nm square is 0. And finally we subtracted nc square. So here nc square minus nc square is 0. So in the total in this side of the equation we left with 0. What about the other side of equation number 3? In the other side we have already added this expression. mb square plus nm square minus mb square, so we copied it as it is. Then we added to this side of equation number 3 nd square, then we added to it nm square, and then we subtracted nc square. Then we took out d square second factor from nd square and also from nm square. Inside the brackets we left with only n plus n. Then we took out mn second factor from mn square and also from nn square. Therefore inside the brackets we left only with m plus n. And we have minus mb square minus nc square. Then we added to this equation number 3 mb square and also nc square. And we found out that d square m plus n plus mn times m plus n equals to mb square plus nc square. Then we took out m plus n, the second factor, from those two expressions. So inside the brackets we left only with d square plus mn, that is equal to b square m plus c square n. We have already found out in the first method that m plus n is a, so we substituted m plus n by a in this side of equation number 3, and we found out that m plus n is a. Inside the brackets we have d square plus m times n, that is equal to b square n plus c square n. And this is exactly Stewart's equation. So we succeeded to prove Stewart's equation in two different methods. Okay, thank you very much.